This is the 25th video in our series on topology, and today we're going to build up to something called the fundamental group attached to a topological space. So let's dive into the starting point. So let's say we're given paths f and g, and so recall that a path is just a continuous function from the unit interval into a topological space. And here we have the setup where f of 0 is x0, f of 1 is x1. So that means f is a path from x0 to x1. And then g of 0 is x1, g of 1 is x2. So that means g is a path from x1 to x2. Now we want to define the product of these paths. And so we'll call it star, so f star g. We'll go from 0, 1 to x, and it'll be defined by f star g of t is equal to f of 2t if t is between 0 and a half, and g of 2t minus 1 if t is between a half and 1. So the idea here is you just do the f path, and then after you're done with that, you do the g path in that order. So starting at time 0 and ending at time 1. It's just you have to speed up along each of those paths to finish in the unit interval. And so, well, this is a path from x0 to x2 because it's kind of clearly continuous. It's like gluing those old two paths together. And here's like the picture. So here we have in yellow our path f. In this peach color is our path g. And then f star g is going to be this magenta path. So we want to first show that we can lift this kind of star operation to homotopy classes. In other words, we want to show that if f1 is homotopy equivalent to f2, g1 is homotopy equivalent to g2, then f1 star f2 is homotopy equivalent to g1 star g2. But that means that this star operation can be defined on the equivalence classes like this. Okay, so let's get to that. So let's say that f and g are the homotopies, and I guess I should say capital F and capital G are the homotopies for f1 to be equivalent to f2 and g1 to be equivalent to g2 respectively. And so let's recall really quickly that that means that f is a continuous function from 0, 1 cross 0, 1 into x, such that f of 0 comma t is equal to f1, and f of 1 comma t is equal to f2. And then a similar formula for our g's. So g goes from 0, 1 cross 0, 1 into x. And we have g of 0t is equal to g1, and we have g of 1t is equal to g2. So we somehow want to glue these two things together into something that will be a homotopy for f1 star f2 and g1 star g2. Okay, so here's how we'll do that. So let's define this thing that we'll call h, and it's got to go from 0, 1 cross 0, 1 to x. And, well, we need a formula for it. And it'll be like this. So h of s comma t, so it's going to be a piecewise function, f of s comma 2t, and this is going to be when t is on the interval from 0 to a half. And then it'll be g of s comma 2t minus 1, and this is going to be when t is on the interval from 1/2 to 1. So let's check that it works. So let's do h of 0 comma t, but then inserting 0 in everywhere we see s, that's just going to give us f of 0 comma 2t, which is equal to little f of 2t, or sorry, little f1 of 2t. And this is going to be when t is between 0 and a half. And then here we'll have g of 0 and then 2t minus 1, which is little g1 of 2t minus 1. And that's going to be when t is between 1/2 and 1. But observe that that's exactly the piecewise definition of f1 star g1 evaluated at t. And then, well, via a very, very, very similar calculation, you'll see that h1t is equal to f2 star g2 evaluated at t. But that means that this h is our homotopy between the product of f1, f2, and g1, g2. Okay, so let's move on. Okay, so now for a big definition. So a loop based at a point x naught is a path that simply begins and ends at x naught. So that means it's a continuous function from the unit interval to x, where x naught is f of 0 and it's f of 1. Now, something like this can really be thought of as a function from s1 to x, because essentially what's happening here, since f of 0 is f of 1, is we could glue the domain into a circle, but that's not what we're going to do here. Okay, then the fundamental group of our topological space X relative to x naught in X is, well, we're going to call it pi 1 of x comma x naught, and it'll be the set of all equivalence classes of F, and that's homotopy equivalence classes. Okay, so here's the idea. Here's our space X. Here we've got a loop F, which is based at x naught. We have another loop G based at x naught. And if you star them, you're going to get F followed by G. That's like the operation here. So notice that still gives you a loop based at x naught. Okay, so, well, what do we need to do? We need to show that this is, in fact, a group with operation star. Okay, so how do you show things are a group? Well, you need an identity, you need inverses, and you need to show associativity of the operation. So let's start with the identity. So let's define e sub x naught, and so this is going to go from 0, 1 into x, so that e sub x naught evaluated at t is simply always x naught. So this is a pretty boring loop. This is just the loop that stays stationary at x naught. It doesn't go anywhere. And so maybe let's point that out. This is going to be for all t on the interval from 0 to 1. And now let's observe that if we do the star operation of f with e sub x naught, and then evaluate that at t to get a formula for it, given the fact that we had the star operation on the previous board, we get something like this. We get f of 2t, and then that's going to be t on the interval from 0 to half, and then we'll be sitting at x naught when t is on the interval from 1/2 to 1. Okay, so the idea here is we have our loop. So let's say this is our point x naught, and then this here is our loop defined by f. Perhaps it looks like that. And so generally what happens is you would just travel along this loop in that 1 minute or 1 hour or 1 unit of time. But if you do this star operation, what happens is you go faster, you travel along this loop in 1/2 unit of time, and then you sit at the end point. So for this to be the identity, we don't need this to be equal to the original path. It's in fact not equal to the original path. Because, like I said before, this is the path where you go faster and then you sit at the end point for the last half hour, if you will. What we need to show is that this is homotopy equivalent to our original path. And of course, you would need to show the same thing for ex star or ex naught star f, because we may not have commutativity here. And that would be like sitting at x naught for half an hour and then rushing through the path in the remaining half an hour. We'll just show one of them. Okay. So let's define the following function, which will become our homotopy. So we'll say f of st is equal to this. So it's going to be a piecewise function. So it's going to be f evaluated at 2 over 2 minus s times t. And this is going to be when t is on the interval from 0 up to 2 minus s over 2. And then it'll be x naught for t on the interval from 2 minus s over 2 and 1. And so depending on s, recall that s is between 0 and 1 here, s determines how long you sit at the station, if you will, after you've done your loop. And so let's see, what we should have is that f of 0 comma t is perhaps going through this at normal speed. It takes an hour to walk on the path. And then f of 1 comma t should be the case where we walk it in half an hour and we sit for half an hour. That would be this f star e sub x naught. And then the things in the middle would be like, oh, maybe we, for instance, take 45 minutes to walk along the path and then sit for 15 minutes. Perhaps that's what's happening when s is somewhere between 0 and 1. Okay, so let's check that this works. So let's do f of 0t. So that means we're going to plug in 0 everywhere we see s. Okay, so that's going to give us f of 2 over 2 times t, in other words, f of t, when t is on the interval from 0 to 2 over 2, which is 0 and 1. And then we'll be at x naught when t is equal to 1. In other words, when it's on the closed interval from 1 to 1. But this is continuous because we know f of 1 is equal to x naught. So this, in fact, turns just straight into f of t as needed. Now let's look at f of 1 comma t. And let's observe that that gives us the following. So that's going to give us f of 2t when t is on the interval from 0 to 1/2. And then it'll give us x naught when t is on the interval from 1/2 to 1, as needed. But let's observe that that is exactly f star e sub x naught evaluated at t. So that means this capital F is a homotopy. But what does that mean we've proved? We just proved that f is homotopy equivalent to f star e sub x naught. But that means that inside of pi 1 of x comma x naught, we have the equivalence class f is equal to the equivalence class f star, the equivalence class e sub x naught. But that means that e sub x naught is at least acting like a right identity. And then maybe as a homework exercise, you can check that if you do e sub x naught star with f on the left, you'll get the same thing, which means in the end, this e sub x naught is the identity. Okay, cool. Now what we need to do is show that we have inverses. Okay, so now to go for inverses. So for a loop f from 0, 1 to x, let's define f bar, another loop, by f bar of t is f of 1 minus t. So this essentially just reverses the time. So let's get a picture going here. Let's say that this is our point x naught again. So let's get that there, and let's say that this is our loop f. So let's see, f is going in some sort of counterclockwise rotation. But then what will f bar be? Well, f bar will be the same path, but it's that same path in the clockwise rotation. So it's just going one direction around a circle, if you will, or another direction around a circle. Okay, so now let's compose these things and see what we get. I guess I should say take the product of these. And so let's note the following, and that is if we do f star f bar evaluated at t, here's what we get. And this is going to be after replacing f bar with what it is in the function, just for what it's worth. So this is going to be f of 2t when t is on the interval from 0 to half. We know that that's the case. And then it's going to be f of 2 minus 2t when t is on the interval from 1/2 to 1. Okay, so like I said, I replaced the f bar in here with its definition above. And so what is f star f bar doing? So let's see. So it's simply traveling along a path twice, once in one direction and once in the other direction. So maybe we could draw this and see what's happening. So perhaps what would happen is you would do F like this, and then that would take 1/2 hour. And then after that, you would trace in the reverse direction, and that would be F bar. That would be doing F star F bar. You go around one way, then you go back around the other way. So what we need to do is somehow make those two ways cancel each other out. And here's the idea. So since we're going around this way, and then we're going back around this way, it means that if there were like two ghost versions of ourselves, they would run into each other. And we want to take that place where they run into each other and turn it into like a turnaround point. So the idea here is this. So let's say this is our point x naught. So perhaps we would unfurl this a little bit at a time. So we would turn around right before we hit x naught. And then maybe we would do that again. So do the loop again, but turn around even further from hitting x naught. And then we would continue to do that over and over and over again until we actually never leave x naught. But we want to do that via a homotopy. So let's see which function makes that work. So let's define f of st like this. So it's kind of goofy, but it all works out. So this is going to be 2t when t is on the interval from 0 to s over 2. And then it's going to be f of 2s minus 2t, and that's going to be when t is on the interval from s over 2 to s. And then after that, it's going to be simply equal to x naught. So that's going to be when t is on the interval from s to 1. Recall that s is between 0 and 1, so all of this kind of makes sense. Okay, so now let's observe the following. So let's observe that f of 0 comma t is going to be what? So it's going to be equal to f of 2t when t is on the interval from 0 to 0. Notice that this first interval collapses when s is 0. Well, this second interval is also going to collapse. So we're going to have f of minus 2t when t is on the interval from 0 to 0. And then finally, we'll have f is simply equal to x naught when t is on the interval from 0 to 1. But observe that that is exactly the function e x naught t. It's the identity function. So now let's look at f evaluated at 1 comma t and make sure that everything works. So that's going to be f of 2t when t is on the interval from 0 to half, just plugging in 1 where we see s. And then it'll be f of, let's see, that'll be 2 minus 2t when t is on the interval from half to 1. And then it'll be x naught if t is on the interval from 1 to 1. But that's actually not a problem because this thing is equal to x naught if you plug in t equals 1 anyway. So that makes it continuous. But observe that this is equal to f star f bar evaluated at t as needed. Okay, so putting these things together, what did we just show? Well, we just showed that f star f bar is homotopy equivalent to ex naught. But if it's homotopy equivalent to ex naught, that means that inside of the fundamental group, well, what we're defining to be the fundamental group and showing as a group right now, we have the homotopy class of f star, the homotopy class of f bar is equal to the class for ex naught. In other words, these are inverses of each other. And then I guess if you wanted to, you could check that they are inverses in the other order as well, but I'll leave that for you. Okay, so we've got identity, we've got inverses, now we need to show associativity. Okay, so for associativity, we need 3 paths on x, based at x naught. Now, I'm gonna form the star product, well, I don't have it on the board anymore, but the star product with 2 different associations. And we'll see that we do not get the same loop, but we will be able to find a homotopy between them, showing that when we push to the fundamental group, we in fact have associativity of the operation. Okay, So I'm going to write this down. If you want to check all of the details for this, it shouldn't be too bad. So if we've got, let's do it in this order, f star g, and then star h, and then evaluate that at t, you get the following. So this is going to be f of 4t, if t is on the interval from 0 to quarter. And then after that, it's going to be g of 4t minus 1 when t is on the interval from quarter to half. And then it's going to be h of 2t minus 1 when t is on the interval from half to 1. Now notice that this makes sense because we starred these two together first, which means we halved their intervals already. And then starring it with h, we'll have their intervals one more time, which is why the intervals for g and f are half the interval for h. Okay, so now let's compare that to f star g star h. And then I'll just write that down. Again, you can work out the details. It's not too bad. I think these are kind of clear. So let's see, that's going to be f of 2t when t is from 0 to half. So notice that here, the interval for f was only halved once, but the intervals for g and h will be halved twice. So we're going to have g of 4t minus 2 when t is between 1/2 and 3/4. I need to shift it a little bit more because even though it's the same length of interval, it is shifted. And then let's see, we'll have h of 4t minus 3 when t is on the interval from 3/4 to 1. Okay, so now we need to find a homotopy between these. So I'll write it down and then you can check that it does what we want. In other words, if you plug in s, you'll get one of these. I believe it's this one. And if you plug in s equals 1, you get this one. So in other words, s equals 0 will give us the top, s equals 1 will give us the bottom. Okay. So let's see. This is going to be f of 4t over s plus 1. And then down here, it'll be g of 4t minus s minus 1. And then finally, h of 4t minus 2 minus s all over 2 minus s. So it's kind of gnarly, but this all works out. And this first one is going to be when t is on the interval from 0 to s plus 1 over 4. And then down here, this is going to be when t is on the interval from s plus 1 over 4 up to s plus 2 over 4. And then this last one is going to be when t is on the interval from s plus 2 over 4 up to 1. So again, that's the homotopy. I'll let you check that when you evaluate it at the appropriate places of s, everything works out. Okay, so in the end, we have everything we need for this fundamental group to actually be a group. Okay, so now let's see what we can do with it. Okay, so now we're going to start looking at some really interesting properties. So let's say that alpha is a path from x0 to x1 inside of our topological space X. Then what we'll do is define something called the induced homomorphism associated to this continuous function. We'll call it alpha hat. And it'll be a homomorphism from the fundamental group of x based at x0, or relative to x0, to the fundamental group of x relative to x1. And we'll actually show that this is an isomorphism. So we're going to define it as follows. So alpha hat of this equivalence class F will be alpha bar, the homotopy class of that, star the homotopy class of F, star the class of alpha. So I guess I didn't put down what we're proving here, but this is an isomorphism. So an isomorphism of groups. So what this tells us is that as long as we've got a path between 2 points, the fundamental group based at the path kind of doesn't matter. Okay, so let's check that it has the homomorphism property first, and this is pretty straightforward, and then we'll argue immediately that it's an isomorphism. Okay, so let's do alpha bar of F star G. I really mean the equivalence classes of each. And so that's going to be alpha bar star F star G star alpha. And so that's by our definition here. But now what we'll do is we'll sneak in an alpha bar alpha between F and G. And then just to highlight this, I'm gonna put some parentheses. So I've got alpha bar star F star alpha. And then that's gonna be starred with, let's see, alpha bar star G star alpha. Okay, good. So let's see, what I did is I inserted this alpha alpha bar, but we know that those are going to be inverses of each other. I guess we didn't properly prove it in the case that you're outside of a group, but that is going to be homotopy equivalent to the appropriate identity map. It's similar to what we just did. Okay, but now observe that this is exactly what we want it to be. It's going to be alpha hat of F star alpha hat of G. But that means that alpha hat is a homomorphism. Now, how do we show it's an isomorphism? Well, let's notice that alpha bar hat is another homomorphism, and not only is it another homomorphism, but is its inverse. And I think it's pretty clear that it's its inverse. So that means we've got an invertible homomorphism, but that means it's an isomorphism because invertible means that, in fact, we have bijectivity and injectivity. Okay, so that proves that this is an isomorphism. Okay, so let's keep going. Now let's suppose we've got a continuous map between topological spaces. We'll call those spaces X and Y, and H will be our continuous map. Then we'll also suppose that H of X naught is Y naught. Then let's define H star to be a map from the fundamental group at X, or of X, relative to X naught, to the fundamental group of Y relative to Y naught by the following formula. So H star F is equal to the class of H composed with F. Now we want to show that this is a group homomorphism. So I think this is a really nice result that continuous functions between topological spaces can be lifted to group homomorphisms in their fundamental groups. So this is really nice stuff. So here's kind of the picture. So we've got this loop inside of X based at X naught. We've got this loop inside of Y based at Y naught. And then this function H is taking the loop in X to this loop in Y. I guess the loop in Y is really defined by the loop in X. Okay, so let's first show that this is well defined. That's always important whenever your domain is made up of equivalence classes, and this is the case here. Okay, so let's suppose that the equivalence class of F is the same thing as the equivalence class of G. But that means that F is homotopy equivalent to G. That's kind of the definition of that. But that means that there exists an F from 0, 1 cross 0, 1 to X with the stuff happening that we want to happen. So F of 0t is F of t, and capital F of 1t is equal to G of t. Okay, nice. But now what we'll do is we'll set capital G equal to our little h composed with F. And let's observe that this does what we want it to. So G of, let's see, 0 comma t is equal to h of F of t, just by definition. And then G of 1 comma t is equal to h of G of t by definition. So that tells us that yes, indeed, h of F is homotopy equivalent to h of G. But that tells us that the classes are the same. So the equivalence class of H composed with F is the same as the equivalence class of H composed with G. But that means that they are equal inside of the fundamental group, meaning that we have this H star of F is equal to the H star of G, as needed to show that this thing is well defined. Okay, now let's show that it's a homomorphism. All right, so let's show this is a homomorphism now. So let's look at H star, and this is like underscore star, I guess I should say, of this F star G. So we want to show we should be able to factor this. But notice that that is the same thing as our map H star of the homotopy class of F star G by one of our first results, today at least. But now that's going to be the homotopy equivalence class of H composed with F star G. Again, by the definition of our H star map. But now there's this thing where H composition will distribute over this star map. I'm not going to check that. I'm actually going to leave that as a homework exercise. And that's going to give us the following. So this is going to be equal to H composed with F star H composed with G, like that. But now we can split those up into the class of H composed with F star, the class of H composed with G, but that's exactly what we want it to be. That's going to be our map H star evaluated at F, and then starred with our map H star evaluated at G. But that's what we need for this to be a homomorphism. Okay, here's an important corollary of this result, and that is if X and Y are homeomorphic via this homeomorphism that takes X naught to Y naught, then the fundamental groups are isomorphic. So this follows immediately from the result right here. We'll just use a homeomorphism and its inverse, which will push to a homomorphism and its inverse, making that homomorphism an isomorphism as needed. Okay, so now before I leave you with some exercises, here's like the big picture of what's going on here. And I think we can clue into it a little bit more if we say that H star is equal to pi 1 of H. So that means that pi 1 will be like a function, if you will, that takes topological spaces to groups, and it takes continuous functions to group homomorphisms. Okay, so up here on the top, we've got a continuous function from X to Y. And then down here on the bottom, we've got a group homomorphism between two groups. And what's linking all of this together is this pi 1 map that assigns X to a group, it assigns Y to a group, and it assigns a continuous function to a group homomorphism. So what's happening here is we're seeing something called a functor. And well, the functor goes from this category of topological spaces to the category of groups. All right, here's some exercises. So the first is to carefully check that H composed with F star G is homotopy equivalent to H composed with F star H composed with G. And thus, as equivalence classes, we have the following equation as needed for that proof that we did. Then let's show the following, which is actually required for the corollary of the proof that we did, but I'll let you fill in those details. So let's say that H and K are continuous functions, H from X to Y and K from Y to Z, where those are all topological spaces. Furthermore, we have H of X naught is Y naught and K of Y naught is Z naught. Then the star operation works like you would like it to. In other words, if you do K composed with H, that's going to be a continuous function from X to Z. But if you star it, you get a group homomorphism from the fundamental group of X to the fundamental group of Z. And that's equivalent or equal to the composition of the group homomorphisms K star and H star. But let's observe we could write it like this. We could write it as pi 1 of K composed with H is pi 1 of K composed with pi 1 of H, leading more credence to this categorical idea that we talked about before. Okay, finally, let's say that alpha is a path from X0 to X1 and beta is a path from X1 to X2. Let's show that alpha star beta hat is beta hat composed with alpha hat, where recall that hat was the induced homomorphism from a path, or the induced isomorphism from a path. And that's a good place to stop.